Caramel. Is the presentation visible? Okay. Good evening, everyone. Hope you all had a good weekend. So today we'll be starting with unsupervised learning. And in unsupervised learning, we'll be seeing both clustering and something called dimensionality reduction. Okay. So to start with, can anyone tell me the difference between supervised and unsupervised learning? When I was giving an introduction to machine learning, I talked about four different paradigms. So what's the difference between supervised and unsupervised learning? Anyone? I hope you all remember it. The difference between supervised and unsupervised learning. The major difference in terms of features, labels, anything you can think of. Okay, so the answer here is supervised learning. You have both your features and your labels. The labels can be discrete. That will be classification. If it's continuous, it's regression. In the unsupervised learning case, what you're doing is you don't have any labels, but you want to have a prediction about the class. Again, the email spam case, you don't have an annotated data set where for training, okay, that this email is spam, this email is not spam. So you have the trained data set with annotated labels, but in the unsupervised learning case, you won't have that. You might have to do it on your own with just knowing the features alone, seeing the patterns in the features that you define. Right? And this is basically the difference. Here, supervised, you have two classes. In the case of uh, maybe this is an SVM, you try to find the maximum margin hyperplane that separates the two classes. If it goes below this line, it's class 0. If it goes above this line, it's class 1. Okay. Here is the unsupervised learning case where you don't have these labels. Labels are these circles and projects. You don't have the labels, but you want to separate them into two different classes. See, this forms what I would say is a cluster. These points are very, located very near to each other. Any points that fall in this circle might also have similar properties. Okay? And likewise for this cluster also. But when you check the difference between these two, they are far apart in terms of features itself, and they might have different levels. That is the intuition behind unsupervised learning. So this is a very easy case. We can visualize it and separate it into two different clusters. Okay, but what about some points are here, some points are here. You don't know how many classes are even there, and so on. And if you think of the higher dimensional case, we can only visualize it till 3 dimensions. What if it goes beyond that? Okay, how do we cluster them? How do we do unsupervised learning? That is what we are going to learn in this class. Okay, so first clustering. Uh, so it is dividing the data points, into any number of groups that you define. Okay, and clustering typical applications would include, your social networks like Facebook, Instagram, shopping preferences, and market segmentation. Um, Market segmentation, I would say, how do you, cluster your customers so that you can give them recommendations based on their taste. Okay? Because previously you won't have any idea how this customer would buy which product. Okay? But based on his age, based on his social network data, you can kind of identify he or she which product he or she is most likely to buy. Okay? That is one of the applications here. Again, Instagram or Facebook, you get these suggested, friends or something. There also clustering is used based on your previous network, based on your other data. They come to a conclusion that, hey, this you might know this person, so you can give him a request. Uh, Everything depends on clustering, and there are many different algorithms that do clustering. So the approach here would be, so the objective here is to classify all data points into separate clusters. Okay. And uh, and inside that, inside those separate clusters, classify everything as single cluster. Okay. And these models, just by visualization, you can interpret. Okay. How, how much distant those clusters are. But again, if you go on to very big data sets, the problem there would be, you can think of this as a KNN based approach also. You have to calculate something called the distance metric between that specific point and other points surrounding it. So when you go move on to large data sets, these methods are slow and you won't be able to get anything useful out of them. So these are the types of clustering models. First one is the centroid based models. And in specific, we'll be looking into k-means clustering in this class. Okay. Then we look at other things, let's say distribution models and density models. You don't need to go into the details of these two models. You'll only be focusing on centroid models right now because this involves a lot of mathematics. Okay. So this is the step-by-step implementation of how you do k-means clustering. Okay. Can anyone uh, recall how we did k then the steps involved in k nearest neighbors? Can anyone put it in the chat or speak up? How did we do k? The KNN algorithm. Anyone? You can go through the previous slides and also answer. That is not an issue. Okay. Okay, and then you have your features, you have your labels, you get a test point, and you calculate the distance. Anyone remembers what distance we calculated at that point while discussing K and N? What was the distance metric used? Anyone? It was the Euclidean distance, right? The sum of square of the distance. Okay. So again, what we do here is get the concept of centroids. Okay. Calculate the distance between data points and centroids. Again, how do you calculate the centroids? Anyone? Centroid in a triangle, or you might have learned it in your high school. Okay. So centroid, you calculate the mean distance of the points present in that cluster. Okay. I think it would be better if I show you a visual example. Okay. So these are your data points. How many clusters do you think can be separated into? How many clusters? Which one do you think would be ideal in this case? Number of clusters. Just give me any number. Yeah, two. That that would be the best. I can also do it this way. This would be a cluster, this would be another cluster, this would be one, this would be one. So any number of clusters you can. Okay. But let's go with two for now. Okay. In this, I would assign any point to be the cluster center. Okay. Yeah. Any point to be the cluster center. Okay. Take this point and this point. What I would do is, okay, calculate the distance of all the points with respect to this point and calculate the distance for this point and all the points. Okay. After calculating the distance, what should I do? Like K and N, what should I do? I should assign it to that specific cluster that is closest to this point. Okay. So, this point. Okay. Which cluster should I assign it to? Is it closer to the red one or closer to the blue one? That point is closer to the red one or closest to the blue one? Okay, just by looking at it, you can say it is closer to the red one. Okay, it's very far from the blue one. Okay, so I would assign this point to the red cluster and this point to the blue cluster. And similarly, I look at how close it is to which specific cluster, red one or blue one. Okay. See, I mark all the points that are closest to the red one as red, all the points closer to the blue one as blue. Okay. This is the end result. What I would do again is I would discard those, calculate the centroid of the red cluster. What is the center point in this cluster? Okay. And likewise, what's the center point in the blue cluster? Okay. Then I move this point to this point. Okay. This has become my center and this has become my center. Okay. The first phase is over. Then you keep repeating this step. You keep on repeating this. Let's do it once more. I calculate the distance, change my assignment. I would say cluster assignment like this. Once this is done, calculate the centroid of this specific cluster and this specific cluster. I move my center again. Again, I calculate the distance. Then do assignment. Okay. Then I try to move the centroid again. It just come here. And after this phase, there would be no change in my cluster assignment. Okay. This point will be closer to blue only and not closer to red anymore. So I stop it there. Okay. Once the cluster assignment or labels don't change, I will stop the iterations. Okay. Any doubts in this? K means clustering. Any doubts? Everything is clear. Initially, I don't have red and blue. I want to separate it as red and blue. I randomly pick some points, randomly. Okay. Calculate the distance. Whichever is closer, I will assign it to that specific red or blue cluster. Once that is done, I calculate centroid again. Move this point here. Move this point here. Redo the entire step. Okay. Until the labels don't change between those points. Okay. So, yeah. So, what are the pitfalls or disadvantages? Okay. First one is, I would say, local optima. Okay. This would be this is the ideal case that we want. But if we pick a point here and red here, it will get stuck. Okay. If I randomly choose points, what happens is, if I choose these 3 points, then everything is fine. 3 separate clusters are there. Okay. But what if I choose both the random points here itself? The red will get stuck here, green will stuck here, get stuck here, and this will be an entire bigger cluster. Okay. And what if I choose a point here? There won't be any clusters for red. That is what I mean by getting stuck in a local optima. Okay. You have to carefully choose the points also. Where do I place the initial point? The algorithm entirely depends on where you place the initial cluster point. Okay. Then the Second one I would say is choosing the value of k. K here represents how many initial points or how many classes I want. Okay. Here I could have gone with two, I could have gone with five, I could have gone with one, not one, I could have gone with six. So how do we choose the best value? Any idea? How do I choose the best one? How do I choose the value of k? Again, you might have a small data set containing the labels. Okay. You check, you put those test data points and see which cluster or label it belongs to. Okay. Then see if it is correct or not for a fixed set of points. Okay. Then the third one is works when on clusters having a spherical shape. Okay. Again, if you have a cluster having this specific shape, it's easier for it to cluster. And if you have it like this, it's very hard. Okay. These are some of the disadvantages of k-means cluster. And how to select k? So one is the elbow method. Okay. What you see is, what you can calculate is if you don't have any labels with you, you find something called the intra-cluster distance. Okay. How close it is to the centroid. Okay. I would say this is the intra-cluster distance. Okay. You calculate this metric. Okay. So you calculate this and select the best one where you select the specific thing. Okay. You get the specific curve. You have 9 different Ks. You have so here the sum of square distance is higher. Here it reduces to here, and it keeps on reducing as you keep increasing the number of clusters. Which one do you think is the best? Which number of K should I select? Okay. Here I would select K as 2 because if you keep increasing the number of clusters, you will go to the overfitting case. You want a trade-off. Okay. So here I select this 2, also known as the elbow. Okay. Looks like an elbow, right? So I'll select this 2 and I'll use it for further steps in my downstream task. This is how you select K. So any doubts in K means clustering? There are other clustering methods like hierarchical or agglomerative. So those are kind of advanced topics in machine learning that I won't be going into. So any doubts in K means clustering? I hope there are no doubts. Okay. Then the other kind that I was talking about initially was dimensionality reduction. So your features can have you can have how many ever features you want. Okay? But why do I want to reduce it? So the number of features essentially depends, is your dimension. Okay. So why do I want to reduce the dimensional reduction? That's what we'll be looking at now. So this is something that comes under multi-area data analysis. Okay. Data analysis is something where you get very much, insights into the trends, patterns, and relationships between your features and your data. And a very simple beginner data set in machine learning is known as the iris data set. Okay. You have four different features: sepal length, sepal width, petal length, and petal width. Based on this, you will guess which type of flower it belongs to. Okay. So you have setosa, virginica, and versicolor. So those are a different species. Based on these measurements, you have to decide which species that particular flower belongs to. Okay. So what happens here is this is what I would say is a pair plot. Okay. Can you what it does is, so here is your sepal width, here is your sepal length. Okay. It takes only these two features and has their corresponding label also. Uh, so what you can try to visualize here is how discriminative the features are. Okay. Discriminative is, I would say, how much well the classes are separated using only these two features. Okay. Can you try to, look at this plot in detail and tell me which pair of features I should use so that all these three, species are well separated? Which one should I use? Which two feature combinations? You can, look at this center, you know, this diagonal, and also compare the peaks. Which peaks are far apart? Which feature combination gives me, peaks that are far apart? Okay. I would say petal width is a good feature since it has well, defined separation between the classes. And if you combine it with, I would say petal length or any of these three features, petal width and sepal width, petal width and sepal width, petal width and petal length. So this would be a better, I would say, combination of two features. But what if you want to visualize the combination of all these four features? Can we do it? Can we visualize it in four dimensions? Yes or no? 4D visualization. Can we do it? Can we visualize anything in four dimensions? 2D, this is the 2D case. This is the 3D case. What about 4 dimensions? Can we do it or not? Okay. Obviously, we can't visualize anything no more than 3 dimensions. Okay. But what if you want to get insights based on combination of all those 4 features? You want to reduce these 4 into 2 dimensions or 3 dimensions and get these kind of insights. Okay. This is why we want to perform dimensionality reduction. Okay. This is one of the objectives of dimensionality reduction. And the first algorithm we are going to look at is something called as principal component analysis. Okay. Main purpose is identify patterns hidden in data. And also what I want to do here is reduce the dimensions so that I can project it, let's say, this 3 dimensional case into a 2D case so that I can visualize it well. And I also have properties similar to that feature space. Okay. Whatever properties are there in the 4 dimensional space, I should also be able to visualize it in the 2 dimensional case also. So that's where this minimal loss of information and representing data comes from. Okay. Moving on, the overall approaches, you have the data set with only features and no labels. Okay. The second step is to compute mean for every dimension of the whole data set. And then I'll compute covariance matrix, I'll compute eigenvectors, eigenvalues, sort the eigenvectors, and transform data set to a newer subspace. Don't worry about this. I'll be detailing it step by step. Okay. So this is what my data set is. Okay. I have 2 classes. I can visualize it in 3 dimensions. Okay. I have 40 samples. I have 3 features and 2 labels. Okay. The problem of multivariate analysis is visualization. Okay. You can't visualize anything above 3D. So I'll start with a simple 3 dimensional example. And my goal is I will drop 1 dimension. I want to visualize it in 2D. I want to convert this 3D space into the 2D space. That's my current goal right now. Can we do it? Anyone? What's one simple way of doing it? I have 3 features. I want to convert it into 2. What can I do? Anyone? Any idea? Okay. The simplest idea I can think of is just drop one of the features. Okay, I'll just drop one. I don't need that feature at all. But if I drop one, the problem is I can't, make use of that feature in any way. Okay. Information is essentially lost, but I don't want any loss of information. Okay. The other thing I can do is take some linear combination of feature and convert it into 2 dimensions. Okay. I'll combine 3 features in a linear way. Linear way is if I have features x1, x2, and x3. Let's say my first feature can be a1 x1 plus a2 x2 plus a3 x3. That will become my first feature. Then the second can be b1 x1 plus b2 x2 plus b3 x3. I want to find what is a and a1 a2 a3 and b1 b2 b3. That's it. My job here is done. I'll convert those three into two dimensions. Okay. And that is what essentially PCA does. So first thing is compute the mean vector. Okay. How many dimensions do we have from the previous example? How many dimensions? How many dimensions do we have? So how many mean vectors should be there? How many means? For each feature, I want a specific mean. Okay. So I'll have three means. And this is essentially how you calculate. Mean is just taking average of all the features. Okay. You have three dimensions, so you'll have three means. That is how you get the mean vector. Okay. Then the second thing I have to do is compute the covariance matrix. Okay. If you take this specific example, you only have a single variable here. Variance here represents how a single variable is distributed. See, this is one, this is another one. Okay. How much spread out the data is. Okay. Based on the, so if your data is spread out across, if it's spread out like this, you have more variance. If it's like this, you have lower variance. Okay. But what if two or more variables come into the picture? Okay. That's where covariance comes here. So I have two variables, x and y. I want to know how these two variables are related to each other. Here is variances. I can say both covariance with itself. Okay. Uh, and here, if x has low variance, okay, here is x, here is y. See how the spread is here. It's not spread out much across x, but it is spread out across y. If variance is low for y, the data is spread out like this. Okay, there's not much variance in y, but x has a lot of variance. Okay, here I define something called the positive covariance. Okay, positive is both are varying by some quantity, both x and y. So it's like this positive. If it's negative, it's like this. Zero covariance. Okay, I don't have any relation between x and y, and this is how my data will be spread out. Okay. Covariance matrix essentially defines how two variables are related, and if you want to visualize it, how the data is spread out. Okay. And these figures essentially give you a summary of that. Okay. Any doubts still here? Okay. The third step is get eigenvalues and eigenvectors. Okay. Eigenvalues here represents how much spread is there in the data. Okay. And eigenvectors determine the direction of spread. Okay. In this case, my eigenvalue is 1. So there is not the magnitude of spread in data is low. And my direction is this. Okay. Similar case, here my eigenvalue is higher. So you can see how much spread out it is. And this is my direction. Okay, these are my directions. Same case here. This is my direction of spread, and this has the magnitude also. Okay. So eigenvalues and eigenvectors you get from the covariance matrix only. Okay. You get it from the covariance matrix. You have the eigenvalues here. You have the corresponding eigenvectors. Eigenvectors give you the direction of spread. Eigenvalues give you the magnitude of spread. See, this is for our case, the data in our case. Okay. This is the spread in this direction. So for each direction, you determine the magnitude of spread. Why do we want to do this? Why do you want to calculate the eigenvalues and eigenvectors? Anyone? If you want to drop one dimension, I want to capture whatever patterns are there in the original dimension space. In 3D, if I have this pattern of spread, in 2 dimension also, I want the same pattern of spread. And eigenvalues and eigenvectors are essentially a way to do that. Okay. This is a slide about matrix factorization. Yeah, you don't need to worry about it. So what I want to do here is you have a large table. I have 5 features. You calculate the covariance matrix. What will be the dimension of covariance matrix? It will be 5 cross 5 because you want to calculate the variance between pairs of variables. Okay, so you'll have 25 values here. From the covariance matrix, you get your eigenvalues and eigenvectors. You sort it based on the magnitude of eigenvalues. Okay, you do that. You get this. You see how the spread is. Okay, here I want it in 2 dimensions. So I'll only take the top two vectors. Okay, top two vectors. This is my transform data and this is my transform table. That's it. Okay, your PCA is done. Any doubts? Mathematics, it's too tough to um, understand. Coding is little bit. Coding is actually easier. Scikit-learn already has this PCA class. So yeah. So you want to convert this larger table into smaller table so that you can visualize it in 2 dimensions. That is essentially the objective here. Okay, for PC. And these are my results. This is my 3 dimension converted into 2D. Okay. This gives you visualization and see if you can actually separate the two classes or not. Okay. You can do one kind of separation. You can get a cluster like this, you can get a cluster like this. Although it's not perfect, the transformation is always not 100% perfect. Okay. There will be some loss of information, even though it is minimal. You can't cap. Even if in the 3 dimensional case, you can actually have separate distinct clusters. When you visualize it in 2D, it may not have that. Okay. That is one of the pitfalls of this specific algorithm. Okay. Any doubts for PCA? Okay. Finally, so this is the summary. I want to reduce that large table into a smaller table, okay, so that it can be easily visualized and analyzed. And I want to select the top K components are this as defined. Top K means here top two in this case. If you want to convert from 3D to 2D. Okay, this is the summary. Then The final thing I'm going to discuss here is about partial least squares. Here, it is not an unsupervised learning method. Okay, PCA is unsupervised because we didn't have any label come into the picture, but partial least squares makes use of the labels also. So this is a supervised technique. Okay, see here, this is your my 3D data. Here I can see distinct clusters. Okay, like this and like this. Okay, and there are two classes, orange and blue one. If I do PCA and do the transformation, I'm not able to get any distinct clusters. But if I also have class information, if I pass in, while doing PCA, I'll also tell this, hey, this point belongs to class one and this point belongs to class two. I'll also supply this information along and transform it into 2D. See, I can get distinct clusters. It's easier for visualization and you can actually capture the truth. Whatever is there in the higher dimensional feature space is also captured in the lower dimensional feature space. So whenever I have labels, I'll use PLS. If I don't have any labels, I'll use PC. This is the gist here. Okay. And here with PLS, you can build something called the correlation plot, where you can associate each feature with the label and say hey, which feature is more important for predicting which label and something. Okay. And which feature contributes more to which principal component that you can get from the correlation plot. And here you get variable importance scores. These are your different features. Okay, higher the score, I can say like this feature is most important. I should not drop this feature at any point. I should make use of this feature in my algorithm. You don't need to. So this is the transform from 3D to 2D. You get these separate clusters, and that will be your biplot. Okay. So summary of PLS here is it is a supervised method. It combines features from both principal component analysis PCA and linear regression. It has the highest predictive power. And what happens is it can actually capture the direction of data. The eigenvectors and eigenvalues I was talking about. And if you also include the labels, it can capture the higher dimensional data well in lower dimensions. Okay. And that's it for today. After this, we can move on to coding. Any doubts? PCA, PLS, gaming, question. Any doubts? Any doubts, or can I move on to the coding part? Okay, I will share my Jupyter notebook. Okay, I hope my Jupyter notebook is visible. Okay. First, I load the necessary packages. Okay, I don't have Angular. Let me just install it. So I load all my necessary packages. And before you do any machine learning, before you apply any machine learning techniques, what you want to do here is do pre-processing and scaling. Okay, this is my original data. I want to use a standard scaler and make it centered around zero so that you can make use of all these ML algorithms more effectively. Okay. Here is your standard scaler. I can transform this data like this. I can use the min-max scaler, robust scaler, and normalizer. Okay. Ideally, I would always want to use the standard scaler. Okay. Before you deal with any data in machine learning, use the standard scaler from scikit-learn and transform your data so that it's centered around zero. Okay. This is one. And let's visualize how k-means works. Okay. These are my initial data points. I don't have any cluster assignment. Okay. I'll randomly pick 1 point here, 1 point here, and 1 point here. Okay. First, I'll assign points based on distance. Okay. It's like this. Then I'll recompute the centroids. After computing centroids, my point changes from here to here, this center. Then I'll recompute, reassign the points based on distance. Then I'll recompute centers. The center has moved from here to here. Then I'll reassign points based on minimum distance, recompute centers again. And if I do it another time, the clusters won't change. So I'll stop it here. Okay. This is just like what I showed in this slide. And if I want to plot the decision boundaries, see, whatever falls in this region belongs to blue. Whatever points fall in this region, it belongs to green. And whatever points fall in this region belongs to red. And these are my decision boundaries. And decision boundary, how do I get it? If I calculate the distance from, let's say, this point and this point, this center and this point, the center of this cluster and this point will be closer. So I'll obviously assign it to green only, since it's far away from this center. Okay. And this is how you calculate it for each point and get the decision boundary. Okay. I'm generating some random synthetic data. Okay. And I'm assigning it three clusters. Okay. Three different labels. I use the k-means class from scikit-learn, do it. Again, you do fit, you define the model, you fit, you predict, and let's see how it is. You see, these are my three clusters again. If I keep changing my k, I change it to 2 and I change it to 5. Okay, these are my labels. This is yellow, this is green, and this is white. If I keep changing the n clusters variable from 2 or 5, see, this is my 3 cluster case, this is my 2 cluster case, and this is my 5 cluster case. You see how much difference there is? And let's deal with some real life data where this is where you have data from patients hospitalized for depression. So there are three variables. One is simplicity, fatalism, and whether they have depression or not. Okay, let's look at it. Okay, by ID column, it's not useful. You get info, what is the type of variables, and you get all the statistics here, the count, the mean. Okay. And I want to look at the relationship between all these features. I showed you in the slide, right? The path plot. Essentially, I'll be doing the same here, SMS.path plot. Okay. I don't have any classes here as such. Okay. So that's why you don't see those three different colors or two different colors. Okay. This is how my data is essentially distributed. Okay. I'll use scaling, the transformation I was talking about here. Okay. Before doing any machine learning, apply the scaling. Okay. After getting this, I'll apply scaling here. Then I'll plot the elbow plot. Okay. This is the elbow plot. Which one should I select? Anyone? Which one should I select? I should select three here. Okay. And if I take the number of clusters as three here and do fitting, let's see how it is. Measure here. Think there is an error with this code. I'll fix it and include the one that is correct. Okay. Like this. So this is your box plot. I think you would have learned about it in your data visualization class. You have three different classes, and these are your features. Okay. And you can see if you take n clusters as three, there is a difference between these three classes. Okay. This will help validate whether you have chosen the right number of clusters or not. Okay. And these are my clusters, three different clusters. Although some points are, in this cluster, you won't always get those perfect separation that was, that was shown in the initial example. Okay. And let's try with k-means 2. Uh, I think this won't run. This. With 2 also, you get some sort of separation based on the blocks plot. And if I try plotting the graph, this is also kind of good. It's not the best k that you get, but again, you have to get k based on the elbow method only. Okay, visualization always does not result in getting you the best k. Okay, and there are more examples for k-means clustering in this specific notebook where you'll explore what happens for this is the digits data set, okay, where you have different where I was talking about the MNIST case where you have different digits between 0 to 10, okay. You have the pixel values and you have to check whether you can actually separate the digits or not into 10 different clusters. Okay, that's what you'll be checking out here. I have uploaded the notebook. I'll fix this specific block and upload it. And you have different metrics to evaluate the performance of k-means clustering here. Okay. And yeah, this this is the I would say the pitfall case or failure case here. Okay, where you have you have taken k-means, you have taken it as two clusters. Okay, it should actually be three. This is not essentially a very good decision boundary since the data set is not, I would say, spherical. Okay, this is one of the failure cases of k-means. Okay. Any doubts in k-means? I'll fix this example and upload. We can all try with different end clusters, different scaling methods, and other things. But any doubts? Okay. Mm, So tomorrow I'll be going through the PCA code, Principal Component Analysis code, and I would like to set up a hackathon in Kaggle tomorrow. So make sure you have access to any laptop. By today, I want you all to create an account in Kaggle. I put it in the chat box, okay? So what I'll do there is I'll give you all, I'll upload a sample data set, okay, where containing different features. Okay, I want you all to try different models that have been taught to you till now. You using the scikit-learn package. I want you all to do hyperparameter optimization using grid search or random search. Okay, and I want uh, to come up with the best model possible. Okay, you can treat this as kind of a hackathon. Whoever gets the best possible accuracy will be the winner. So maybe tomorrow we can try that. So it's better if you all create an account in Kaggle so that we can conduct it tomorrow. Make sure you have access to your laptops. I'll create the hackathon today and I'll first complete PCA and the rest of the unsupervised learning codes tomorrow. And yeah, if you have any doubts, you can ask, or else I think we can end for today. Thank you everyone for attending. See you all tomorrow.